All right, let's get started. So welcome to our last SETS talk of the semester. We're going to start back up as usual in February. So for the schedule of next semester's talks, just be sure to check our website, scienceunderthestars.org, as well as our Facebook group. We'll be posting information up there. And speaking of next semester, I'm happy to announce that we're going to be moving back to in-person SETS talks at BFL. So once again, please be sure to just check our website and Facebook group for just updates on that. We're probably going to try to do a bit of a hybrid approach, at least initially, just so that those of you that are more comfortable joining us virtually can do so. But we will also be placing some mitigation techniques in place to prevent the spread of COVID. So we'll be posting all of that information on our Facebook group and website. So just be sure to stay tuned there about that information. As for tonight's talk, as usual, please feel free to send Julia any questions you have as she gives her talk down in the chat. I'll make sure we go through all those questions at the end. Yeah, so tonight I'm pleased to introduce Julia York as tonight's speaker. Julia actually grew up in Fairbanks, Alaska. She then got her bachelor's and master's degrees from the University of British Columbia in Canada. Her master's degree was on the physiology of high altitude birds. And so kind of fitting with the topics she might talk to us about tonight. She's now a PhD candidate in both the Department of Integrative Biology as well as the Department of Neuroscience. And her research really asks questions about the evolution of animal sensory systems and temperature sensitivity in a ton of different organisms, including poison frogs, fish, and birds, as you'll learn about tonight. So not only is Julia also an excellent researcher in our department, she also has a passion for engagement and science education. She's actually one of the co-presidents of SUTS, in case you didn't know that, among many other involvements that she has. So tonight, Julia is going to convince us that birds are cooler than us. And I'm very excited to hear this. So please take it away, Julia.
Great. Thank you so much, Anne. That's so nice. And yeah, it's just been a real pleasure to organize this event over the last few years. One of the highlights of being in grad school here for me. And thank you guys all for coming tonight. I'm really excited to talk to you about really just some of my favorite bird facts. That's what we're going to hit here, including maybe the first one, which is why I have this title the way it is, because I couldn't just say why birds are cooler than you, because of course birds are not, maybe you know that birds have are warm-blooded like us, but they actually have warmer body temperatures than we do. They're more like 106 degrees Fahrenheit, so that's 41 degrees Celsius, where as we know we're around 98.6 degrees Celsius. So that's a difference between us and birds. So they are figuratively cooler than us, but not literally. This is a little picture of a bar-headed goose chick that I took in college. We'll get to bar-headed geese a little bit later in the talk. First, I want to just go through a little outline of what we're going to talk about tonight. So the first thing, and this is really the takeaway message here, which is that birds are dinosaurs, and I feel like it should be a general topic of conversation. And then we're going to move on to how birds breathe and why should we care about that? Why does that matter? Then we're just going to talk about some cool birds and some interesting things about birds that I think are fun. And finally, at the end, I think I'm going to try to convince you that we should maybe appreciate our grackles a little bit more than we do. Okay, first, so birds are dinosaurs and everybody should be talking about it. So I think when we think about dinosaurs, you know, we think two main things about them. And the first one is that dinosaurs are really large. And sure, they could be really big. These here's a scale drawing of representatives of each of the 5 major groups of dinosaurs compared to a little human here. And you can see that they're quite a bit bigger than we were, and they include some of the largest animals that have ever walked the earth. They could be up to 36 meters long or 118 feet. That's the sauropods, these very long ones that are shown in red here. We actually measure dinosaurs by length, not by height, because they're sort of leaning over on their fore limbs. And they could weigh up to 100 tons. So this is obviously an estimate. Nobody was ever able to put a dinosaur on a scale, but the highest estimates of dinosaur weight is around 100 tons. And to put that into perspective, blue whales, which are currently the largest organisms on Earth, can be up to 100 feet, and they can weigh up to 150 tons, which of course is a little bit different when you're swimming around in water rather than walking on Earth. So we think of dinosaurs as really large. And the other thing we think about when we think about dinosaurs is that they are really dead. And sure, a lot of them are really dead. You know, they dominated the Earth during the Mesozoic, starting about 250 million years ago. And then, of course, ending famously in a major extinction event 65 million years ago that begins the Cenozoic era. And so maybe you know where I'm kind of going with this, which is that really dinosaurs are not completely dead and they were not always large. But how do we know that? And we really know it primarily from fossil data and also from genetic data, modern genetic data. And we use that data to feed our understanding of the relationships between organisms that exist on Earth today and that have existed on Earth in the past. And we do that by kind of building basically family trees. And so I kind of want to take a step back from this for a second and just talk about family trees to make sure we're sort of all on the same page. So, you know, if you look at a family tree, you might start with you or this is just an example of a family tree. You know, this could be anybody. I know like every family tree looks different. I know mine looks different than this. This is just an example. But you might have, you know, a sibling or more and a couple of parents in your immediate family. This is who you're most closely related to genetically. And then of course you have your grandparents and aunts and uncles and cousins that are a little bit more distantly related. And then you have great grandparents and you know, you might have there might have been an uncle in the past who never had kids, you know, and so this sort of lineage, as we might be able to think about it, or line, you know, doesn't continue into the future. And then you might even have more distantly related relatives like second cousins and cousins once removed, great aunts, great uncles. And we can kind of lay it out in this map of how related you are and the relation between everybody. And that includes a dimension of time here, right? So the more distant in time people here we're showing lower, and then the more recent are up at the top. You know, and what do you have in common here with your cousins and your second cousins? It's that you have an ancestor in common, right? You have a common ancestor. And you know, maybe you're able to build your family tree back many more generations and you find out, you know, you're related to Cleopatra or something like that. And how did you figure that out? You figured it out by building in each of those steps of the people older and older until you got, you know, to as far as you could go, maybe, or as far as you had evidence for. And we can do the same thing with groups of species, and that's just on a larger scale. So I want to show you the dinosaur family tree here now. And so they had a common ancestor here of all dinosaurs that evolved 250 million years ago. So again, here we have the time scale where lower here is older and then higher is more recent. And you can see this ancestor divided into several branches. We have the 5 major groups of dinosaurs up here at the top, and they can be split into 2 major groups, the Saurischians and the Ornithischians, which differ in their pelvic bone morphology. And you can see that birds are nested right here in amid all the dinosaurs. So they are dinosaurs, and we've been able to fill in that family tree using fossils. It's almost actually completely filled in between modern day birds and ancient dinosaur ancestors. And you can see the way that that evolution has taken place just using fossils, and then being able to compare modern genetic data and sometimes ancient DNA. You can show that birds are right in the middle of the dinosaur family tree. But then, of course, you might notice that there's an event here where all the other dinosaur lineages have stopped. So right here at 65 million years ago, all of these branches come to a sudden end, but birds don't, and they continue on into the present day. So we have our modern dinosaurs around us today, which are birds. So let's talk about this famous extinction event, the Cretaceous Paleogene extinction event 65 million years ago. You know, I think when we think about this event, we might picture something like this, you know, fire, and we know that it was caused by an asteroid striking the Earth off the coast of Mexico. And certainly maybe it did look like this for a short amount of time, but actually this extinction event lasted at least 10,000 years. So it was a long time in terms of the life of a single organism in order to try to survive this extinction event, which is why it was so difficult. And estimates go up to 80% of species on Earth at that time died. And that's because of the crater and the asteroid hitting the Earth. Aerosols were thrown into the air, sulfuric acid, and that caused acid rain and reduced sunlight for probably decades, if not more. And so actually this extinction event probably looked a little bit more like this. And it was very difficult for organisms to survive during this time. Of course, this is the 5th major extinction event that we know of on Earth, but we're in the middle of the 6th one right now, and I'll talk about that a little bit later. Okay, so let's get back to birds and how they were able to survive. Actually, that's not really known. I've read a couple of things about how it might have been that they have beaks and that they were able to process seeds, and seeds were a source of food that stuck around when plants and animals were dying. But birds are really interesting within the dinosaur family because they're part of the theropods, which are meat-eating dinosaurs that had upright ancestors, and that includes like the Velociraptor and the Tyrannosaurus Rex. And if you follow this, some of those obviously were quite large, but if you follow along the bird lineage, the birds are actually really very small for dinosaurs. So they've the average size of a tetraneurin, which you can see is right here at this branch, was quite large. And then as you go along the branch towards birds, they become smaller and smaller. And birds are actually one of the smallest dinosaurs. And they have another quality about them, which was really interesting, that evolved around here, around the Maniraptora, when these animals were evolving, and that's feathers. And so how do we know that they evolved feathers? Well, we can actually see it in the fossils. So this is a fossil from southern China, and this is an ancestor of a dinosaur, you know, an ancient dinosaur that maybe was related to birds or was an ancestor of birds. And you can see that it has feathers here running along the whole side, and you can see the imprints of the feathers in the fossils, which I just think is amazing. And not only can you see it in fossils, but actually there are some labs that go into amber markets all over the world and have been able to find preserved dinosaur tails in amber. So this is an example of a 99 million-year-old dinosaur tail found in amber, and you can see that it has feathers on it. And if you zoom up on these feathers, they look almost just like modern day feathers. So this is an example of a duck, a close-up of a duck feather from today, and you can see they're very, very similar. Okay, yeah, so I hope, when you really take that in, that birds are really just tiny dinosaurs, and they're around us all the time. We have this amazing diversity of birds around us, and they're very charismatic, and they're our little dinosaurs. And you might even have eaten some dinosaurs for dinner tonight. I'm not sure. Okay, so yeah, let's talk about the modern birds, and let's talk specifically about switch gears and talk about how they breathe. So you might think, birds breathe. Of course, they breathe like me, like all of us right now, in and out into their lungs. And, we have lungs that are inflated with a diaphragm that look quite a bit like lungs from amphibians and from reptiles. This is a little drawing of a mammal lung like ours, they're quite sort of sac-like, they're the air goes in and then it goes back out, and they expand and contract and act both in doing that and bringing the air in and out, and then also in the actual gas exchange, the oxygen going into your blood and carbon dioxide coming out. But actually birds look totally different than that. So this is a little drawing of a bird respiratory system, and you can see it's completely different. So they have a lung here, which is shown in purple, which is relatively small and relatively rigid compared to ours. And it's actually ventilated by these air sacs that come off of it that do not participate in the exchange of oxygen and carbon dioxide, but instead sort of act as bellows to ventilate the lung. And the lung sort of doesn't really contracts and expands very little with each breath. And so the lung in birds is very specialized just for the gas exchange. And then they've sort of separated the function of the ventilation, the bellows, into these air sacs. And so what does this actually look like in a real bird? So this is a CT scan from a bar-headed goose that I did for my master's. And you can see the bones here in yellow of the bird and the little outline of the body. And then you can see the lungs in red here, which are quite small and adhere to the ribs at the back of the bird. And then the blue is the air sacs. And so it takes up quite a large percent of this bird's body volume. In this particular bird, it's 46% of the body volume of the bird at maximum capacity. And they can be quite extensive. And just a little callback, there's actually evidence that dinosaurs as well had air sacs in the same way. Just like birds, they had air sacs and lungs separated. And you might think, well, of course you aren't able to see that in a fossil, but the air sacs are actually continuous with the air spaces in the bones. So a lot of birds have hollow bones, as we know, and the air sacs are actually connected to those air spaces in those species. And so when these other dinosaur species, not bird dinosaurs, but other dinosaurs, when we have, which would have been continuous with air sacs. Okay, so how does this work? So this is a little drawing of a bird respiratory system, and it's has the head side over here and the tail side over here. And this is the trachea, which goes to the mouth and the little voice box of the bird. And then this red part is a schematic of the lungs. and the blue here are the air sacs. So when a bird is breathing, we'll actually follow this little cloud as an example of just one breath of air as it moves through the bird. And so on the first inhale, it goes through the bird to the air sacs at the back of the bird, at the air sacs at the tail end of the bird on the first inhale. And then on the next exhale, that breath goes through the lungs of the bird, all in one direction. And that's the important part. It's going all in the same direction. And then on the next inhale, it goes into the front part of the air sacs in the front part of the bird. And on the next exhale, then it goes back out of the bird. And this actually occurs all with aerodynamic valving, not physical valves. And it allows the air to move in one direction through the lung and almost continuously as the bird is breathing. And so if you're following one breath of air, it actually takes 2 breaths or 2 breath cycles of the bird for that breath of air to go all the way in and out of the bird. Okay, so why does this matter? Well, if you're able to send the air all in one direction, then the animal is able to control the direction of the blood relative to that. So in a mammal lung like ours, where the air is all just coming in together and the blood that goes to our lungs is kind of going all different directions, you're getting sort of a mix. It's not very directional. And so that means that the maximum amount of blood oxygen that your blood can get to is that of the air that you're exhaling. So whatever your exhaled air is, that's as high as your blood oxygen can possibly get. But in a bird, because the air is all going in one direction and continuous, they can send the blood in a perpendicular direction. So that's called countercurrent flow. And that, because of diffusion, allows the blood oxygen to go higher than that of the exhaled air. And it actually ends up at an amount between the inhaled and exhaled air. So this is a little drawing of kind of what that looks like. So here's the blood all going in one direction and the air going perpendicular to that. And you can see that the air might come in with 100% of the oxygen and the blood comes in with 0% of the oxygen. And then as the blood is leaving the lung, it has, more like 65, and which is actually higher than the amount of the air that's leaving the lung. So that's pretty great. And it's actually, so it's much more efficient than our system, but it's actually not even the most efficient way that vertebrates can breathe. Actually, fish gills are even more efficient than this. So they have completely cross-current ventilation where the water is passing over the gill in one direction and they send the blood in the complete opposite direction. That's called cross-current. And that allows the blood oxygen to actually approach that of the inhaled water at this point. It's not air, it's water. And that's really great for fish, because there's not, it's harder to get as much water or it's harder for them to get oxygen than out of the water than it is for us to get it out of the air. Okay, so this allows birds to be really efficient and in getting oxygen when they're breathing. And so they're just kind of generally better at extracting oxygen and surviving in situations where oxygen is low. And there's a classic study by Tucker in 1968 where he just put a sparrow and a mouse in a chamber and then drops the oxygen to simulate about 6,000 meters, which is about 20,000 feet. And the mouse went comatose. They're not able to serve or to stay awake for this, but the sparrow was fine, totally unaffected. And this isn't even one of our more impressive birds. So now I want to take a little moment and ask you a few questions. So if you want, you can just drop your answers in the chat here. And the first one is, how high do you think a bird can fly? What is the maximum height that a bird has been able to fly that we know of? So go ahead, drop them in the chat, or just talk amongst yourselves about them. And then the other one is, how long can a bird fly without landing, continuously without landing? And the next one is, what is the most metabolically expensive, so what's the most energetically demanding form of locomotion? And by locomotion, I mean running, swimming, or flying. And that's and I'm asking for all animals, not just birds. Okay, I wish I had some like Jeopardy music here or something. Okay, these are some good guesses. Awesome. Okay, so let's start with how high a bird can fly. So the highest, the record right now is held by this charming bird, the Rupel's griffon vulture. And one of these guys was unfortunately sucked into an airplane engine at 11,000 meters, which is 36,000 feet. And that's really amazing because they were flying where there's only 25% of the oxygen that's available at sea level. They were like sadly identified by a tail feather that was stuck in the engine when the plane landed. Okay, next, how long can a bird fly continuously without landing? And the record for this right now is held by the common swift. You know, we don't have common swifts in Texas, but we do have lots of swifts in Texas. They're quite beautiful. And these guys can fly for 10 months continuously. They breed in Northern Europe and Scandinavia, and then they take off after breeding and fly to sub-Saharan Africa, where they spend most of their year flying around eating bugs and things. And they've, you know, not all of them fly continuously during that time, but they have found at least, they were able to tag these birds and found 3 of them that did not land for up to 10 months that whole time until they return back to Europe to breed. And so they just stay on the wing all the time. Okay, and last, what's the most metabolically expensive form of locomotion? This is actually kind of a bit of a trick question because it depends how you measure it. So as you might have guessed, flying is the most expensive, but that's only per unit time. Whereas actually running is the most expensive per unit distance. And so if you think about it in terms of like, if you have to move for 1 minute, then you're going to use the most energy flying to go for that minute, but you're going to go further. Whereas if you have to go 1 mile, it's actually going to be more energetically efficient to fly 1 mile than it is to run 1 mile. It's going to go slower. Okay. And so, but this makes these feats of these birds that are able to fly for so long even more amazing. And I want to tell you about one more amazing feat that some birds are able to do, which is again, we're coming back to the bar-headed goose, the picture I took of a bar-head. And these guys have one of the highest altitude migrations of any bird species. They actually spend their winters in India and then their summers breeding in Mongolia. And so to get between these 2 places, they have to fly over the Himalaya. And they actually have been doing this migration since before the Himalayas were this high. And as the mountains have pushed up over evolutionary time, this migration has been pushed upwards with them. And so this is some data from Lucy Hawkes in 2012 that they tagged these geese in Mongolia, and then we're able to follow their whole route over a year. And so each one of these colored lines is the path of a goose. And from where they tagged them here at this black arrow over the mountains. And you can see they actually don't, these white X's are the highest peaks in the mountain range. And the white line in the middle here would be the most direct route that they could take. And so they don't actually take the most direct route. They go a little bit to the side of it in order to not have to fly over the highest peaks, but they still, still do this, and this is made all the more amazing. But if you look at the altitude profile of one of these flights, so this is one of these, how this bird flew over the altitude, and you can see they go from India, which is right at sea level, up to the Tibetan Plateau, basically all at once in one flight that's 12 to 16 hours. They go from sea level to 5,000 meters, which is about 16,000 feet. Although the whole migration takes them about a month or two, but they do this one gain in altitude all in one go, all in one flight. And they're able to do that because of their really efficient respiratory system, something that we would not be able to do. Okay, cool. So now I want to talk about another bird, a little bit different, not about the way they breathe and their respiratory system, but actually something I recently learned about, which I just want to share with you, which is, did you know that there are poison birds? So this is a hooded pitohui, which they live in Papua New Guinea. They're sort of these beautiful black and orange colors, and they're poisonous, just like poison frogs in South America. And for the same reason, they eat beetles and insects that produce toxins, and then they spread it on their feathers, and so they're actually toxic. And they've been able to evolve resistance to toxins such as batrachotoxin, which are these toxins that are in the beetles, and so they're can get away from predators by that. Isn't that cool? And not only are poison birds in Papua New Guinea, but actually there used to be poison birds in the US as well. So this is the Carolina parakeet, which is extinct now, but used to be distributed here in the Southeast US. And actually it was the only parrot native to the US. But it went extinct in 1918 due to habitat loss. And it's actually one of the top candidates for the process of what scientists want to do called like de-extinction, where, you know, they take the genetic material and try to revive this species, because I think they have, you know, they have birds in museums and stuff, and maybe could be able to rebuild their genomes. So these were our very own poison birds here in the US. Okay, and now I just want to talk quickly about extinctions, because of course this isn't the only bird species that's going extinct, and in fact a lot of bird species are going extinct and are predicted to go extinct in the future. There was a study a couple years ago in 2019 that predicted the rates of extinctions over the next 15,000 years using models from the red list. So these are different levels of concern for extinction. So this is least concern, you know, all the way up to endangered in the red here. And they estimated, they projected, given what the current rate of extinctions right now, what will be the rate of extinctions going forward year by year, and how many bird species will there be in the future, from our current 11,000 down to very few in the future if we keep going at the rate we're going. Of course, this is due to lots of different factors, but primarily due to habitat loss because of humans. And they also were able to show that conservation efforts can make a big difference here. So the dotted line is with no conservation, and then the solid line is with conservation in both graphs. This is actually, sorry, I should have explained. This is actually just a blow up of the first 500 years here. And so they showed that conservation efforts can actually reduce extinction rates by 40%, and that's kind of a conservative estimate, but we really can make a difference here if we try. Okay, so last part of the talk, you know, I want to try to convince you that maybe our famous grackles here in Texas are kind of cool. And for those of you who are here, since we're online, people are all over the place. might not know about grackles, but grackles are our local bird species here, which are very common around Austin and sort of disdained for, you know, let's say soiling people's cars. And there's actually a grackle Yelp page for Austinites here, where people describe them anywhere from, you know, a little weird, a little gross, to you know, completely biologically incorrect flying rats, completely devoid of charm and vaguely evocative of the end times. And then there was also, you know, the classic Yelp comment where they say they scared my girlfriend, and when I made fun of her, she broke up with me. Really has nothing to do with grackles, but thank you for your review. Okay, so I did a little bit of reading about grackles so that hopefully we can appreciate our local dinosaurs here. And the first thing I found out is actually that, you know, as much as there are so many bird species going extinct due to habitat loss, grackles are actually one of the few species that have expanded their range because of humans, and over, you know, as humans have increased urban environments, grackles have been able to benefit from that. And so actually under natural conditions, or aka without humans, grackles experience really high nest mortality, primarily due to starvation and predation from snakes. But when humans are present, they're able to reduce predation of their nests and they're able to find food from us. And so because of that, between 1880 and 2000, grackles have actually expanded their range over 5,000%. And so you can see in this graph that they used to be only in South Texas, and they've expanded north into the US with as urban environments have gotten larger. And in fact, they came to Austin only in 1902. And also in this, I also read that, you know, the grackles have been associated with humans for a long time, and they're actually, and of course we have a lot of bird species that do that, like pigeons, or you know, birds that we see around in the city. But grackles are the only species that do that that are actually native to North America. And they were actually also associated with the Aztecs before, and so they're really our only native North American species that has benefited from us being around. And, you know, how have they been so successful? Well, it's mostly because they're quite innovative. So I also found this paper that showed grackles living in Death Valley. And as you might know, Death Valley is one of the hottest and driest places in North America. It's very difficult for a lot of species to survive there. But these people observed grackles doing a novel behavior, which has never been seen before in a bird, which is eating bugs off of people's license plates in the parking lot. So this is in one of the hottest parking lots in all of Death Valley. And here's a female grackle doing this little behavior where she jumps up and takes insects off of license plates, and they're able to survive in these areas because of that. Okay, so I hope I kind of convinced you that maybe we can appreciate grackles a little bit more, and that's the end of the talk. So thank you so much for listening, and yeah, I'll take any questions that you guys have.
All right, that was great. Thank you so much, Julia. It was super interesting. It does look like we have a couple questions in the chat, so I'm going to just go through them. So first of all, Julia, do you happen to know whether grackles are closely related to crows?
I think they are, in that they're also corvids, and so yeah, they're somewhat related to crows, but yeah, that's as far as I know. Sorry.
I guess behaviorally they're somewhat similar.
Yeah, very similar, very crafty, you know, very smart.
Okay, another question we've got is, what is your favorite bird and why?
Oh, wow. Oh, wow. I should have known that one was coming. Hmm. I mean, I might have to give it to the bar-headed geese because we're like in this picture so so tight. I love them and they're so charming and just amazing athletes. So yeah, I would have to say bar-headed geese.
Makes sense. Okay, what about how are the grackles related to the Aztecs, what you had mentioned earlier?
Oh, I just meant that they were associated with Aztecs, like cities and things like so. Just in the way that you find grackles at higher densities in cities here in Texas, when the Aztecs were around and had, urban environments, the grackles also were concentrated in those areas, and benefited from human behavior in that way.
Got it. Very interesting. Okay. Another question is, what species of bird that is living now goes back the furthest in time?
What species of bird that's living now goes back the furthest in time? I don't know. I don't know the answer to that. I think we can go back and look at the tree, and see that this, the like true birds evolved around 150 million years ago. Whether any of those exact species are alive now, I guess it depends what you define as a species, but yeah.
Yeah, that's a great question. I'm not sure either. Oh, that's a good one. So are there any other birds that have expanded their range like the grackles have?
Yeah. So like pigeons, like starlings, like maybe any kind of bird species that you've heard of that's invasive. That's I think there are some sparrows that have done that. They're able to sometimes expand their range quite a bit faster than grackles are able to. Than grackles have been able to, even though they've expanded quite quickly. I think it's like 3% per year or something like that. But for example, starlings, crossed the whole US from one introduction in like 60 years. So that was like quite a faster expansion of their range, but they were introduced. So it was a little bit of a different situation than the grackles.
Got it.
I love all these grackle questions. This is great.
Now, another bit of a zinger question here is, if you could be a bird, which kind of bird would you be?
Wow. Like maybe I would be a crane because they have those long legs and so they can kind of go through the water. But then they also are very good flyers and can fly very high as well. So you'd be able to like do both, but I wouldn't be against being a penguin either. I think that would be fun. They seem cozy.
So do you happen to know anything about the sort of panting behavior that you might see in Austin in kind of the middle of summer? And someone's asking, if this is kind of like respiration to keep cool.
Yeah, it is absolutely respiration to keep cool, just like dogs pant, or it's trying to cool them off and particularly move air across their beaks. So when birds are overly warm, they put a lot of extra blood into their beaks, and you can see like their beaks get quite hot. Their beaks and their legs are like their primary parts of their bodies that are able to dump heat. And so their beaks get quite warm, and then they're able to rapidly breathe and move air across that beak, and it's also wet because it's their mouth, and so they're able to cool quite efficiently their beak that way. So.
Wow, that's really cool. Okay, Are outdoor cats a danger to birds?
That is my understanding. Yes. And it depends where you live. It depends on how far your cat goes, or, how adventurous your cat is. But, you might notice that your cat is killing birds if they're outside. You might be able to see like what kind of species that is and figure out whether that's you consider that a problem or not. I've gotten into some, let's say, tense discussions with some people about this subject. And, my opinion on it is I think that and it's just my opinion, but I think that having outdoor cats is, a problem for the environment. But of course, we do things that are problems for the environment all the time. I drove to work today and I took a plane the other week, and, we all make those decisions and those trade-offs. So it's just like what you're comfortable with and what you feel like is part of it. But I do think that, that having an outdoor cat is one of those things.
Yeah, I think the estimate is like a couple billion birds are killed a year by cats.
Yeah.
But yeah, that's a great answer, Julia. So, okay, back to kind of the evolution of birds. Did the ability to fly help dinosaurs or birds survive the impact?
So people think not, actually, because there were flighted dinosaurs like pterosaurs and other related, the raptor dinosaurs that were not true birds, that all were able to fly, and those lineages died out as well. And so only really the beaked birds were the ones that survived, the ones without teeth. And so, the thought is that something about having a beak was what was important. And like I said, one of the things I read about it was like maybe that allowed them to eat seeds and specialize on seeds and fruit, or like other sources of food which were not meat, and so were more readily available in a situation where resources were limiting.
Got it. Another kind of question about the oldest species that are extant now is the oldest species of bird in North America.
I don't know that. Sorry. I don't know. I wish I did, but I can try to look it up for whoever that is.
I know the longest lived bird is an albatross, I think.
Cool.
But yeah. Okay, maybe so we have Harold Zakon in the audience is saying an anhinga. Which,
anhingas. Okay, cool.
It's really interesting.
Yes. Those are beautiful birds.
Yeah. Okay, let's see. So on the extinction projection graph that you had, it showed an initial spike in extinctions without conservation. But further down, there was more extinction estimated with conservation. What explains this?
That is a great observation. And I'm not sure. You have to go and read this paper. It's not very long. I didn't read it that carefully, I'll be honest. But so I'm sorry.
Spoken like a true scientist. Okay.
I'm sorry. But yeah, no, that's a really good observation. It does go up and accelerates a little bit. I think it might be due to like that the extinction rate is currently accelerating, and then you're going to get to a point where sort of like all the obvious bird species to die have died, and then it's going to sort of start dropping. So that would be my initial like hypothesis about it, but I'll have to admit that I did not look closely enough at the paper for that question. Sorry.
It's okay. Yeah, I know how that feels. Okay. Okay, so Miles, who's 11 years old, is asking, why do those birds have to migrate at high altitude?
Well, great question, Miles. And I guess, they could go around. Like I said, they've been doing that migration since before the mountains were so tall. And so before, I think it was just the most direct route from their two areas that you know, birds migrate for food, primarily for resources. So between those two areas, that was the easiest way to go. And then as the tectonic plates have moved together, the Himalayas are still rising to this right now. And but it obviously rises quite slowly. And so that, because of the slow rate of change of the height of the mountains, that allows the birds to actually adapt rather than having to force them to make a sudden change and go around. They're able to slowly over time be capable of such a migration, and they have a lot of adaptations that enable that, and there's a lot of people studying that.
It's super cool. So when the asteroid hit, were birds already small to us, like, yeah, body size wise?
Yes. Yeah. The the birds that were around that time were quite small, maybe, yeah, similar to the bird sizes that are now.
So kind of actually related to that as well is you mentioned that their beaks were in part, the birds that survived had beaks rather than teeth. Are there other reasons why birds may have survived when remaining dinosaurs went extinct?
Maybe, yeah. I think it's not known. I think it's it's a mystery. It's a debated thing. Um, I think the hypothesis for why mammalian ancestors survived is that we were able to hibernate and go use low energy states like torpor to survive periods where there were not a lot of resources. And birds are also known to do that. Hummingbirds use torpor or sort of go dormant, kind of like on a daily basis, because they have such high metabolic rates. And so I'd expect that ancestral birds were also able to do that. And so it's possible that could have been part of it, and then when they really needed the energy, they were able to find it because of this seed thing. But yeah, I think it's still debated. I think it's kind of a mystery as to why they were the only ones that were able to survive.
What's so neat about torpor, that always blows my mind a bit.
So cool.
Yeah.
Yeah.
Okay, so there are also obviously primarily aquatic birds like penguins that stay underwater for long periods of time. How do the penguin lungs work compared to other birds? Are there differences there, or?
Yeah. What a great question. I love that question. Yeah. Diving birds are really interesting, and there are some penguins that can dive up to like 500 meters. Emperor penguins can dive really, really deep. And so that, most birds are different than diving mammals in that they dive on inspiration, actually, rather than mammals dive on expiration. So you exhale and then dive. Birds actually inhale and then dive. And so, and it's, thought that they're sort of able to use the oxygen that's in that breath, like as they're diving, as an oxygen store. Whereas that's not good for mammals, right? Because as you use up the oxygen in that air, then it starts to pull oxygen out of your blood if you're not able to control like where the air is going and whether it's at the respiratory surface or not. But birds are able to control that. So they have they have air sacs. Penguins do, just like all other birds. They're able to use that to be able to dive better, and that is a really cool thing. That there have been a couple of studies on that.
That's really
But great question.
oh, that was Harold Dacon. There you go. um, so the Papua New Guinea bird, how does it release its poison?
So my understanding is that it releases it through the uropharyngeal gland, which is the little oily gland at the base of the tail of birds. And you might notice, like when you watch a bird kind of preening, that it wipes its beak on the base of its tail and then goes and like wipes it on its other feathers. And that's because they're getting the oils from that gland and then moving it onto their feathers. And so I think that this bird it secretes those, it eats them. It doesn't produce them itself, but it eats them in the beetles, and then it secretes it through that oily gland and then spreads it all over the feathers.
Got it. And then things that eat it don't like it because it's covered in poison.
Right.
That's cool.
Yeah.
Okay. So do all birds have feathers, Julia?
Yes. Does the person know the answer? Am I wrong?
I think that's right. Yeah.
I'm thinking of like a hairless cat right now, trying to imagine like a featherless bird, but I'm not coming up with anything.
It'd be a bit scary. That's interesting. So the birds, the swifts that you talked about that fly for months at a time, do they sleep while flying?
Great question. Yeah. That's also another thing that people are trying to figure out. One hypothesis is that, they fly very high at dawn and dusk. And so it's thought that maybe as they go, to these really high altitudes and then they sort of drift down, and it's thought that during that time is when they're sleeping.
So they're sleeping while they fall.
Yeah, they're sleeping while they sort of glide down and fall, sort of micro.
So do you think,
hopefully?
do they need to sleep for the same amount of time as like a typical human?
I don't know.
Or do you think it's like short
I guess
bursts?
Not. They're not dropping for 8 hours. So I think probably they're splitting up their sleep in some other way. Yeah. But yeah, the scientists that tagged them and found these that they fly for 10 months, that was like one of their first questions is, when are they sleeping?
Right.
So that was their idea about it.
Neat. Okay, so Susan is saying that she likes to watch a bird in a bird bath. How does getting wet help them? Why do they enjoy bird baths?
That's a good question. I think like anybody, they like to be clean. But I was actually just in a talk yesterday about sensation of touch in birds. And one of the things we kind of talked about was that it's possible that when a bird puts its beak into like cold water, into something cold, that their sense of touch is actually increased and stimulated in the same way that actually happens to us as well. And so, maybe they enjoy it because it like feels good. Or, they kind of increase their sensitivity in their beak when they get it wet or cold and then go to groom. It's just an idea. I don't know. This was just, I was in this talk literally yesterday. But yeah.
That's crazy. That's a really neat idea. Yeah.
I don't know. Maybe, I certainly think that birds like to play in the water and they think it's fun. So.
Okay, so back to grackles. Why do they flock to grocery stores at dusk?
I don't really know the answer to that question. I think it's a social thing. Living in groups, they're obviously very social. They like to come together and talk to their friends about it, But I don't really know exactly. yeah, I'm no grackle expert, but maybe I'll aim to be sometime.
I think I read at one point that it's like a resource thing. So the parking lot tends to have a lot of like crumbs and stuff,
Oh, really?
like
Interesting.
food options. But it seems weird. It
Yeah.
seems like, would there really be
Yeah,
more
like why
than?
parking lots in particular? Yeah, I don't know, but they definitely do, don't they? Like they really like those
Absolutely.
ATV parking lots. That's their spot.
Yes.
Yeah.
um, yeah. So Brian's also mentioning, kind of in line with the Swift thing, that some birds, or all birds, maybe, I don't know, can sleep on one side of their brain at a time.
Hmm.
So I'm not sure. Yeah. Do you think that would help the Swifts if that were the case in
Probably,
them?
yeah. Maybe that's how they're able to, like not actually just plummet. They are able to glide. I'm not really sure. I've heard that as well, and I've heard that about like dolphins and stuff that they're able to do that while they swim. But I don't really know much more about it.
Yeah, it's definitely worth. I'm going to look that up later.
Yeah.
um, well, so that's kind of the end of the questions in the chat. Does anyone
Cool.
else have more questions for Julia? Or Julia, is there anything more you'd like to add?
Great questions, you guys. Thank you so much. This is so fun. Sorry I didn't know the answers to all of them, but I think they're fun to wonder about.
Absolutely. Okay, well, I guess we can stick around for a few more minutes if anyone else has questions. But thank you so much for the talk, Julia. Let's give you a virtual round of applause here.
Thanks,
And
Anne.
yeah, and to everyone who came in a little late, we're going to start back up in February, and it'll likely be in person. So stay tuned for more information about that.
Thanks, everybody.